Hi everybody, welcome to another video in Calculus 1, section 2.6, continuity. The whole chapter we study about limits, and the way we define limits is when x approaching to a number, the function approaching to a limit. Now, and of course what we define is it doesn't matter what happened at the point. It's more important is what happened near the point when it gets close to the point. Right. So this section we try to connect all of those together. So definition of a continuous function. A continuous function or a function is continuous at the point A if the limit is equal to the values of the function. All right. Earlier we said that the values of the function has nothing to do with the limit, or the limit has nothing to do with the values of the function at the point, because the way we define it is getting close to the point. It's a lot more important than what happened at the point. But in this case, if it is continuous at the point, then the limit equal to the values of the function. Right. If it is not continuous, then the point is called the point of discontinuity. Right. So a function is continuous if all three of these must hold. So we need to have all three of these conditions must be true. The function is defined at the point. The limit exists and they're equal. So all three of these have to be true for the function to be continuous at the point A. Right, so all three of them has to be there. A removable discontinuity is a discontinuity that can be removed or by redefining the function at the point. Right, so we'll go over a few more of this. But let's just look at the sample. Based on the definition, identify the values of x on the interval at which f is not continuous, and identify which condition fails. Right. So first of all, loosely speaking, continuous function can be drawn in one stroke. For example, this is a continuous function. You can draw that without picking up the pen. This is not a continuous function. In order to draw that, we have to pick up the pen and draw the second part of it. Or even this consider not continuous because it is missing a point. Right? So again, if we draw a continuous function, we don't really need to pick up the pen. Right? So when we look at this, there will be a lot of different points where it's not continuous. So first, it is at 1, they're missing a point, right? So now this question asks us identify the values of x where the function is not continuous or the function is discontinuous. So we can say it is at x equal to 1. So first of all, at x equal to 1, why it is not continuous. So let's check those three conditions. Is the function defined? That would be no, because at 1 there's no point corresponding to that on the graph. So the function is not defined. The limit exists though. The limit does exist and go to 3. But because the function is not defined, if the function is not defined, we cannot have the last condition. So we say when x equal to 1, f of 1 is undefined. So it's not continuous. We only list the point that is not continuous. Right, so that's the first one. Next, as x equal to 2. At x equal to 2, the function is defined equal to 3. The limit does exist equal to 1, but they're not equal. So at x equal to 2, it is also not continuous because f of 2 is defined limit when x go to 2 exists, but they are not equal. So the third condition fails. Right, so that is at 2. Now at 3, it's also not continuous. Because the function is defined, which is good, but the left side go to that point, the right side go to this point. At x equal to 3, limit does not exist. Limit when x go to 3 of the function does not exist. Actually, I changed the setting of the camera a little dark, but then it is too dark probably. Back to normal then. Right. So x equal to 3, the limit does not exist. Then if one of these fails, the function is not continuous. Right. So next is good at 5. X equal to 5, the limit does not exist, even though we say the limit equal to infinity, right? Because the function approaching to infinity, but infinity is not really a number, so we say the limit does not exist. And also you can say the function is undefined, and of course they're not equal, so all 3 conditions fails. Yeah. So in this function there are 4 points where the function is not continuous. 1, 2, 3, and 5. Now, out of all of this, which one is removable discontinuity? Right. Think about this. It is defined as removable, meaning if we move it, it could be continuous. Now think about this. At x equal to 2, if you move this point down here, it would be continuous, right? So if we move this point here, it will be continuous. Also, even though at x equal to 1, the function is undefined, but if we can define it to be 3, if there's a point here, the function will be continuous. So 1 and 2 here, because we just put a point back in, or we move the point, the function can be made to be continuous by changing the values of the function at that point. So in that case, it is called removable discontinuity. So this 2 is called removable discontinuity because we can add 1 point to make the function continuous. I mean, not adding, or we're redefining or change the values of the function at the point, the function will be continuous. So it is removable discontinuity. Right, so how about the other 2? Right, the other 2, at 3, if the point is already defined there, there's nothing we can make, there's no point we can add to make them continuous, right? Because the limit does not exist. You cannot change the values of the function to make the limit exist, because the limit already does not exist. Doesn't matter what you change the values of the function, the limit still does not exist, and therefore it cannot be continuous. So that's why in this case, when x equal to 3, this is what we call a jump discontinuity. So we have to jump from one value to another. Kind of a term discontinuity. So all there's a gap, if you will. And the last one, all three conditions fail. Yeah, doesn't matter if you define the point, you can add any point here. It doesn't make the function continuous. Once again, if the limit does not exist at the point, doesn't matter what you define the function at the point, the limit still does not exist. So in that case, there's nothing can be made to make it continuous. So it's not removable. And there's also, it's not really a gap here. So the third kind of discontinuity here, when x equal to 5, we call that asymptotic discontinuity. So that is this case number 3 here. So there are 3 types of discontinuity removable, where we can add a point to make it continuous, or we move the point to make it continuous. That is removable discontinuity. The jump discontinuity is where we have a gap in a function. And the asymptotic discontinuity is likely where we have, it's like where we have the vertical asymptotes. So those are the 3 types of discontinuity. Right. Next, this theorem, even though it doesn't have a lot of expression here, but this is extremely important. So it says the following functions are continuous whenever they are defined. Sorry, I typed the note here. Sometimes the grammar and the spelling might be, it's not perfect. Right, the following functions are continuous whenever they are defined. So, polynomial function defined on all real numbers, so it is continuous everywhere. Exponential function, the same way. The root function, everything is good except we have the square root of a negative number. That gives us imaginary. A rational function, everything is good except for when we divide by 0. Logarithmic function defined and continuous whenever, except for when we have log of a negative or 0. Trigonometric function defined whenever, but that doesn't make any sense. I'll change this note and before I post it, so don't worry about it. A trigonometric function continuous. Yeah, I'll change this before I post the note online. Trigonometric function is continuous whenever it is defined, whenever they are defined. Sorry. Right, so, and pretty much these are all the functions we know, right? There's pretty much that. The only function that is not on this list is absolute values, or in general, piecewise function. Which function not on this list? The answer, piecewise function. Right. So it's very powerful. This theorem is. So what we know is that there's a bunch of functions. Pretty much all the functions that we know is continuous whenever it is defined. Meaning that we only need to check the first condition and we can say the function is continuous. Right. Right. So everything's on pretty much all the function that we know except for the piecewise function, including absolute values and step function, all other things. Those are considered piecewise function. Therefore, is exception to the rule. Other than that, all the function we know is continuous whenever it is defined. So how do we do this kind of problem? So when we look at this problem, determine the intervals where the function is continuous. We look at the function x squared plus 1 x squared plus 1 is polynomial. Polynomial is continuous everywhere because it is defined everywhere. 3x plus 5 is also a polynomial which is continuous and defined everywhere. So for x greater than 0 is good, when x less than 0 is good. We just need to check what happened at 0. So let me write this. X squared plus 1 is a polynomial polynomial is continuous everywhere because it is defined everywhere. Which is continuous everywhere. Even though it is continuous everywhere, but for this part of the function, it certainly will continuous for x greater than for x less than 0. And for this particular problem, it's continuous everywhere, but it's not everywhere. It is for x less than 0. So for x less than 0, it is continuous. That's first. Second, the same reason for 2x plus 5, it is also continuous for x greater than 0. Is continuous for x greater than 0. Of course, I base on this condition. So on greater than 0 is good. They said equal to 0 here, right? What happened at 0? Okay, yes. The problem is for the piecewise function, if each of the piece is continuous, which is good, but we need to check the gap. Always have to check the gap. So, and in that case, I said at x equal to 1, I mean at x equal to 0, is it continuous? Okay, we just need to answer this question. Right, so continuous, the function has to be defined, the limit exists, and they have to be equal. So we just need to check those three. First of all, black. X squared plus 1. So first of all, what is the values when x equal to 0? When x equal to 0, it has the equal sign here, so I'm going to put 0 in for x. And it is equal to 1, so it is defined. So that's good. Next, does the limit exist? So piecewise function, what happened on the left, what happened on the right? So on the left, we use this function, limit as x go to 0 from the left side. The left side, when x less than 0, it is x squared plus 1. And if we put 0 in it, it is 1. And then limit on the right hand side. it is 3x plus 5. And if we put 0 in it, it is equal to 5. So since they are not equal to, it is not continuous. So the function is continuous everywhere except for 0, because at 0 the limit does not exist. If limit does not exist, the function cannot be continuous. Right. So when we have piecewise function, each piece, we check each piece, and in this case both of them, each one of them is continuous, but we have to check for the gap. At the gap, the limit does not exist, so it cannot be continuous. In this case, we know for sure this is a jump discontinuity. So determine the interval for the it is continuous. So the answer is we're going to have the interval is from negative infinity to 0, or from 0 to infinity, everything but 0, because at x equal to 0 it is not continuous. So this is the interval where the function is continuous. Be that. Right, next, find the values of the function so that this function is continuous. Alright, we know for sure. Polynomial on the left, polynomial on the right. So continuous on the left, continuous on the right. What happened at the gap? So at x equal to 1. We have the values of the function, which is good. How about the limit? So look at the limit. Go to 1 from the left hand side. The left hand side, when x less than or equal to 1, so I'm going to put 1 in for x. Just write x squared plus a first. And you put 1 in it, you have 1 plus a. So that limit from the left. The limit from the right. On the right, we're going to use this function. And if you put 1 in, 2 times 1 minus 5 is minus 3. Right, so the limit exists if the limit on the left, limit on the right go to the same number. So we just make them equal. So limit exists if the left and the left sign limit and the right sign limit equal each other. So from this we can say a is equal to negative 4. Right. So when a equal to negative 4, the limit exists, and when a equal to, it doesn't matter. When a equal to negative 4, the values of the function is equal to 1 minus 4 is minus 3, and equal to the limit. So let me just write this in conclusion. For a equal to negative 4, limit of the function is equal to negative 3. The values of the function at negative 3 also exists and equal to, at 1. When x equal to 1 plus a is minus 4, so equal to negative 3. So limit and the function equal each other, so it is continuous at a equal to -4. Right. Right. A function is continuous from the left and from the right, so this is the completion. So we might have continuous up to the point or to the left or on the right. Right. One thing I'm not sure if I showed you this before, but if I did, it's good to review. If you want to sketch the piecewise function, you can always do that by graphing x squared plus 1, and then you divide by, this is when x less than, in the calculator we cannot have equal to. It is, but the graph doesn't show it. So I'm just say x less than second math. So we're going to use less than or equal to, I guess it's fine. But less, yeah, it's fine. And then we have 3x plus 5 divide by x greater than 0 and this is our piecewise function. Yeah, because this is not continuous at x equal to 0. Right, so quickly, the reason it works because this is use the logic operation. If we have 3 greater than 0, this is true, right? If it is true, the calculator will return the values of 1. If it is not true, the values will return the values of 0. 1 is true, 0 is false. So back to the piecewise function. If this condition is true, is equal to 1, divide by 1, it will graph this function. If this condition is false, it is 0. When it divides by 0, the function is undefined. Therefore, it will not graph it where the function is undefined. Also here, yeah, when x greater than 0 is true, it will graph it. If x less than or equal to 0, it is false. And false has values of 0, divided by 0 is undefined. And it will not graph the function when it is undefined. So, pretty much that. Right, of course, then we just define the function where it is continuous everywhere in an interval. Right. Next, we have intermediate value theorem. Yes. Sorry, this is another thing that I need to change on the note before I upload online. So intermediate value theorem. You should see this before in coarse algebra or pre-calculus. So it says if the function is continuous on the closed interval a to b and L is a number strictly between the function of f of a and f of b, then there exists at least one number c where the values of the function equal to L. Right. I run out of space there, but this is what the intermediate value theorem is about. So first, the function is continuous from a to b. So from a to b, there. Right? Now, this principle says that if we have f of a and f of b between those two values, f of a and f of b between those two values, there is a line. I see L, there's a value L. If you go from this point to that point continuously, then you have to go through the line. Makes perfect sense, right? If the function is continuous from one point to another and there's a line that between the y values of those endpoints, then the function has to go through it. The graph has to go through it. Right? So if we have this line, so first of all, the function cannot go around it, because if it is like this, it failed the vertical line test, and this is not a function. So because it's continuous function. It is a function, so it cannot go around it. And because it goes continuously, it cannot skip. Because if it is not continuous, you can say the graph go like this, and it can skip the line. Because it is not, because it is continuous, it cannot skip. Right. So if it is continuous and there's a line between the values of the endpoints, y values at the endpoint, then surely we'll have to cut the graph at least one point. Right. Now, if let's say we have the function is continuous from A to B still, and there's a function f of A and f of B. If we have a line here, then the function may or may not cut the line. The graph may or may not cut the line. It may go like this. It cut the graph at multiple points, or it may go like this. Does not cut the line at all. So, if the line is between the y values of the endpoints, then it will cut it. If it is not in between the y values of the endpoint, it may or may not cut it. We don't know. Right, so that is the intermediate value theorem. Once again, I will change that when I post the note online. Right, here's an example. I show that the equation x squared plus 2x minus sin x equal to 0 has a solution between -2 and -1. So it will be easier if we just try to sketch this. So we have the values of the function at between -2 and -1. That terrible graph. Sorry. -2 and -1. Again, that is a terrible graph, but we just ignore that. Right. So first of all, let this be a function f of x. Yeah, don't mind the graph here. Right. Now let's evaluate at -2 and -1, because we need to know the y values of the endpoint, so we can choose the line. I mean, to see if there's a line between those two y values or not. So let's find the y values, the values of the function at those endpoints. So values at -2, the values at -1. Right. Now, to do this with the calculator, make sure if there's trig function, and unless specified, we have to keep things in radian mode. So radian mode in radian. All right. Now, to evaluate this, the easiest way to do this, I just say -2, hit the store key, STO, start to x, and then the function is x squared plus 2x minus sin x. And you have 0.99909. Good enough. Now at -1, I just do -1 store into x, and either you hit the arrow to go up to that function, hit enter, so we'll copy and paste down, or if you are at this step, hit second, enter. It will give the last entry, second enter one more time. That's the function, and you have -0.159. Right. The point here is one of them is positive. F of -2 is positive. And f of -1 is negative. Yeah, it's not a very good graph. So between this point and that point, x squared plus 2x polynomial function is continuous. Sine or even cosine, sine, cosine, those functions are continuous everywhere. So this function f of x is continuous everywhere. So this function is continuous everywhere. Right, so the endpoints are those, and the function equal to 0, so we have 0 is the line. And according to the intermediate value theorem, from this point to that point, going continuously, it has to cut the graph somewhere in between -2 and -1. Right. So because this have opposite signs, because 0 is in between these two values, there will be a values of x between -1 and 2. So let me write this, because 0 is between the endpoint there will be an x between the -1 and -2. There is of values of x such that the values of the function is equal to 0. Right. If y is between these values, there will be an x between these values. That's what the intermediate value theorem is about. Right. Lastly, we do a few more examples. Right. So we'll go over this rather quickly. For what values of x the following function is continuous? So 3x squared polynomial continuous everywhere. E to the x exponential continuous everywhere. So bottom line is what we have to look out for. Let's go back to this page. There are 3 things we need to watch out for. The first one is in even root. This except for that denominator equal to 0, that doesn't work either, and this doesn't work either. So those are the 3 things we need to watch out for, and these 2 functions are not those 3 things, so it is continuous everywhere. Right, next, this one we have the denominator. It is continuous. It is defined if the denominator is not equal to 0. So I will write this function is continuous when it is defined, meaning that when the denominator not equal to 0. For every rational function, that's what we have. Right. Notice the wording here. In the theorem, we say it is except for when denominator equal to 0, or instead we can write it is continuous when it is not equal to. So except for the case equal to 0, everything else is good. And so we just like x squared minus 5x plus 6 not equal to 0, and you can factor out x minus 2 and x minus 3 not equal to 0. So x not equal to 2 and x not equal to 3. Right. The function will be continuous when x not equal to 2 and when x not equal to 3. It has to be n. Because if it's all x not equal to 2, it can be equal to 3. So it cannot be either one of them. Right. Next, this is a radical function or square root. It is continuous. When it is defined. Meaning that whatever inside the square root have to be greater than or equal to 0. So we cannot have imaginary here, meaning we cannot have negative inside an even root. So for x, x greater than or equal to 3/2. So when x greater than or equal to 3/2, the function is continuous. Simple enough. Next, determine if the function is continuous. Right, so we just need to check. In particular, this function is continuous whenever the denominator is not equal to 0. So x not equal to -1 is good. So that part of is continuous. We just need to see what happened at the gap. More often than not, the piecewise function we worry about is what happened at the gap of the two functions. So in this case, we'll find the limit, the values of the function. Values of the function is equal to 0 though, because when x equal to -1. Now we just need to find the limit when x go to -1. So what's that? So let's look at the limit. Look at the function x squared minus x plus 1. Right. When we find the limit, put in the numbers, see what happened, right? Put -1 in for x. Right, -1 squared is 1, 1 minus 1, 1 plus 1 is 2 over 0. Well, that is undefined. But more precisely, when we see something like this, we have to specify if it is 0 from the left or 0 from the right. So let's say if it is from the left side, I'm going to put -1 in here. 2 is still good. So it is -1 from the left. So -1, I will subtract a very small number and store into x. And we have x plus 1 at the bottom. So that is negative. So positive divided by negative is -infinity. So from then on, you can say it is not continuous, for sure. But just to be careful, we do the other one too. When x equals to -1 from the right. Right. Because if we put in -1, it would be -2 over 0, still the same thing. Now if we have the plus sign on the right hand side, so we'll have -1 on the right hand side, so I will add a very small number to it. If it is on the right, we add. If it's on the left, we subtract. Store into x and evaluate the same thing. So it's positive. Positive divided by positive is positive. So the limit in this case does not exist because they're not the same. So if the limit does not exist, the function is not continuous at that point. So this function is continuous everywhere except at x equal to -1. when x not equal to -1, this function is continuous. So determine the following function is continuous. So we said f of x is continuous for x not equal to -1. Right, so that's what we have. So in this section, pretty much what we have is just define continuous function. And the good thing is almost all the function that we learn in the trigonometry with calculus, those functions are continuous whenever they are defined. Except for the piecewise function, we have to check that what happened at the gap. Yeah. And of course we have intermediate value theorem. So pretty much that's what we have. So I stop the section here, and as always, thank you for watching.